So it says connectors in some electrical circuits are coated in gold. One property of gold is its ability to conduct electricity. So that's one reason why gold is used. But give one other property of gold that makes it suitable as a connector. Well, in fact, you can have any of these. First, remember, it is malleable, which means that it can be bent to connect. Also, it is non-corrosive. Gold is unreactive. And you could argue it has a high melting point. But I would think the best one would be it is malleable. So next one says, explain how gold conducts electricity. Well, I've just reminded you here of the structure. So gold has a metallic structure, and the key thing is it has delocalized electrons which are free to move, which carry charge, and the flow of charge is current. So this is how I'd answer this question. Gold has a metallic structure. It has delocalized electrons which are free to move. These carry charge. The flow of charge is current. The next question says, the table shows data from 3 compounds. You've got water, methanol, and ethanol. The first part says, calculate the relative molecular mass for ethanol. Show your working. So you've got the formula here for ethanol. And so we've got 2 carbon atoms. And carbon, if you look at your periodic table on the back of your exam paper, has a molar mass of 12. Plus we've got 5, 6 of hydrogen. And finally, we've just got 1 oxygen, which is 16. And that adds up to 46. The next part of the question is a 4-mark question, and it says, explain in terms of intermolecular forces the differences in boiling points of the 3 compounds. The first thing to remember is these are simple molecules, so we're talking about intermolecular forces. And so we've got 3 intermolecular forces. We've got the temporary dipole to dipole, which is the weakest, which they all experience. Then we've got permanent dipole to dipole, which is for polar molecules. And then we've got hydrogen bonds. Now, if they experience hydrogen bonds, they'll experience the permanent dipole to dipole. And of course, the last thing to remember is if they've got a higher boiling point, then the intermolecular forces will be stronger, so more energy is needed to overcome the intermolecular forces. So why would water be the highest? Well, first of all, of course, a hydrogen bond is made between nitrogen, oxygen and fluorine with hydrogen because they have the greatest difference in electronegativity. So water will have hydrogen bonds. This has got OH, that's got 1 hydrogen bond, and this has also got 1 hydrogen bond. So they've all got hydrogen bonds, but can you see that this has got the highest melting point because that's got 2 hydrogen bonds? Water will have the strongest intermolecular forces because it has 2 hydrogen bonds compared with these ones. Why would ethanol have a slightly higher melting point than methanol? Well, the only other difference would be in terms of the temporary dipole to dipole. And what affects the temporary to dipole is the size or the surface area of the molecule. And can you see this has got 2 carbons and 5 hydrogens, so has a larger surface area. So the temporary dipole to dipole forces will be stronger, which means this will need a slightly larger amount of energy to separate those molecules. So I'll now model what I would say in this exam question. All molecules experience the strongest intermolecular force of hydrogen bonds. However, water has 2 hydrogen bonds compared to methanol or ethanol, so needs the most energy to overcome the intermolecular forces. Hence highest boiling point. All experience the weakest intermolecular force, temporary dipole to dipole. However, ethanol has a larger surface area than methanol, so the temporary dipole to dipole forces will be stronger, so boiling point slightly higher. Silver bromide is an important chemical in the manufacture of photographic film. Potassium bromide reacts with silver nitrate to form silver bromide. Write the balanced equation for the reaction of potassium bromide with silver nitrate. Well, first of all, they've given you the formula of silver bromide and silver nitrate to help you get started. So we're told potassium bromide reacts with silver nitrate. So we've got potassium bromide, well, potassium and bromine. The reason why they've given you these formula is you're not expected to know the charge on a silver ion, but you expect to work out the formula for potassium bromide. So potassium is a +1 ion, it's in group 1. Bromine is in group 7, so it is a minus ion. So that means that that is the right formula. So we've got potassium bromide plus silver nitrate. Also, you should know that a nitrate is a minus ion, and that's in your specification to learn those compound ion charges. So the potassium displaces the silver, so we get silver bromide, and we know that if the total charge on the nitrate is minus, then the total charge on a silver ion must be positive. So we've got silver and bromine, so silver bromide, plus we've got potassium nitrate. And that's plus and that's minus, so that is a formula for potassium nitrate. Now we have to balance it. So if you look carefully, that is already balanced. So silver bromide and potassium bromide both contain strong ionic bonds. State what is meant by the term ionic bond. Remember, all bonds are strong electrostatic attractions, but between what? Well, it's between positive and negative ions, or to shorten it, between oppositely charged ions. A strong electrostatic attraction between oppositely charged ions. Potassium iodide, Ki, is another ionic compound. Draw a dot and cross diagram to show the bonding in potassium iodide. Show the outer electrons only. So we need to draw the diagram for the ions that are formed, and they've already told you it reacts one potassium ion to one iodine ion. If you look, potassium is in group 1, so it's going to lose its outer electron, having a full shell underneath, and it won't be a shell of 2, which will be lithium, it will be a shell underneath of 8. So there's potassium, and I've decided to use dots for the potassium. It doesn't matter, you could have used crosses. I'm going to make it a plus ion because it's lost 1 electron. Iodine is in group 7, it is here, and the iodine will gain 1 electron from the potassium, becoming a minus ion, a -1 ion. And so for the iodine, we're going to draw as crosses, and then just draw that as a dot because that's electron from the potassium. Potassium iodide is soluble in water. A student dissolves 16.6 grams of potassium iodide in distilled water and makes the volume of solution up to 500 centimeters cubed. If you ever see things in centimeters cubed, you know you have to convert it to decimeters cubed. So that will be 500 divided by 1,000. Do that on your calculator in case you make a mistake in the exam, which is 0.5 decimeters cubed. Calculate the molar concentration of the solution produced, and you're told the relative formula mass of potassium iodide is 166. This is so useful, this unit, because that is the unit of concentration, and remember it's moles per decimeter cubed. So concentration is the number of moles per means divided by decimeter cubed, which is the volume. So that's really helpful if you get stuck. So we need to know the concentration, which means we first need to work out the number of moles of potassium iodide we have, and we're given the mass and the molar mass. So the first thing is, remember, the number of moles is the mass divided by the molar mass. So we've got a mass of 16.6 grams, and the molar mass is 166, so that gives us 0.1 moles. We've already converted the volume into decimeters cubed, so finally concentration is the number of moles over the volume. The number of moles is 0.1 and the volume is 0.5, and that gives you an answer of 0.2 moles per decimeter cubed. The electron configuration of an element is 1s2, 2s2, 2p2. Identify the group of the periodic table that contains this element. Well, the key thing is for you to remember in your exam that the S group is group 1 and 2, and the P group is from 3, 4, 5, 6, 7 and 8. So of course 2S is the second period, and then you've got 2P2, which will bring you into group 4. You don't have this in your exam, but you have the periodic table on the back. So try and memorize. Write an equation to show the first electron affinity of oxygen to produce the oxygen ion O-. Remember, the first electron affinity is the energy released when 1 mole of oxygen atoms gains 1 electron to form a mole of oxygen ions. So we have an oxygen atom in a gaseous state gains 1 electron, producing an oxygen ion in the gaseous state. Complete the electron configuration for an oxygen ion. Well, the key thing is to look again at your periodic table and where oxygen is in your periodic table. So if you look, oxygen is here, and an oxygen ion is normally a 2-, but this is when it's gained its first electron. So if you locate that on your periodic table, it's going to have 1 more electron than oxygen, which will be the electron configuration of fluorine. So it is 1s2, 2s2 and 2p, 1, 2, 3, 4, 5. Part C. The graph shows the first ionization energies of elements lithium to magnesium. Notice that the energies go up until you get to neon, with drops at 2 key points. And then you've got a massive drop between neon and sodium going down a period, and then it increases again. Explain the trends in the first ionization energy from lithium to magnesium with reference to energy levels and S and P orbits. So the first thing is you must explain what first ionization energy means, and that's the energy needed to remove 1 mole of electrons from 1 mole of atoms in a gaseous state. So it's removing the first electron from each atom. The first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in a gaseous state. So we can see the rough trend is that the energy needed to remove that first electron goes up between lithium and neon. So we've got to consider, why does it take more energy to remove the first electron? Well, it must be held more tightly to the nucleus. And that's because as you go along a period, the number of protons increases, so your nuclear charge increases, and of course the radius of the atom gets slightly smaller. So that explains the general trend. But secondly, you've got to explain these drops here and here. Well, first of all, remember this is the second energy level going through between lithium and neon. So that's the second energy level. But remember that energy levels have suborbital levels, or suborbital energies. And so this is the S shell, suborbital S shell. Then you go into the P shell. So all of these are in the 2P and those are in the 2S. So you can see that there's a drop when you go from beryllium to boron, because you're going from the subshell S to the subshell P, so they're slightly further away, meaning there's less energy needed to remove the electron from boron compared to beryllium. And then the trend goes up again until here. And we'll explain that one in a minute once we've done these two. In general, the energy needed to remove an electron increases between lithium and neon. This is because the electrons experience a greater electrostatic attraction to the nucleus due to the number of protons increasing along a period. The energy drops between beryllium and boron as the electron in beryllium is the first in the p suborbital, so is further from the nucleus. So the next thing is to explain the drop between nitrogen and oxygen. Remember, first of all, we've paired up the electrons between lithium and beryllium, and then boron, you get a slight drop as the boron is further away because you go into the suborbital of the 2p. Then the electron from carbon is here, and the electron from nitrogen is here. They've all got the same spin. But remember, when you come back to oxygen, you get the first pairing in the p suborbital where you've got the opposite spin. And so there is slightly less attraction now to the nucleus, and therefore that energy drops again. The energy also drops between neon and oxygen, as this is the first electron in the p orbital to be paired up. So the next thing to explain is the large drop between neon and sodium. Well, that's because you're going down a whole period, which means that you've got an extra shell underneath, which increases the atomic radius, so the electrons are further away, but also you've got electron shielding, so the amount of energy needed to remove that electron is less. The energy drops dramatically between neon and sodium, as the electron removed is in the third energy level rather than the second, so further away from the nucleus and shielded by another inner electron shell. Finally, we need to explain the rise between sodium and magnesium, which is because magnesium has an extra proton. The energy then rises from sodium to magnesium due to the extra proton.